right, good afternoon. Just trying to make sure I don't double feedback here with the Patreon post. Cross fingers this isn't going to auto load. Otherwise, do let me know if the sound is good. I've got a fan going in the background because it's kind of butt hot here in New York. If there's too much background noise or if you can't hear me, just let me know down there in the chat. As always, as we go through here. Okay, great. Thanks, JD, for the sound check. As we go through today, if you have questions about any of the topics we'll be discussing, don't hesitate to drop them here in the YouTube. If you're watching after the fact and you want to ask questions, you can drop them in the comments on the Patreon post. You're welcome to try to drop comments on the Patreon post now. I just may not see them in time. They don't auto-load. And then if you have other questions that weren't stated here, feel free to ask them. You may have to repeat them. If you ask in the middle of a question and I forget it for some reason, feel free to ask again as we get towards the end. I'll do my best to answer anything. I just won't have anything prepared. Hopefully it won't be too much of an issue. I do always, of course, want to thank all my supporters over on the Patreon who do make things like this possible. It's a pretty shitty time for everyone out there. And the generosity of people supporting the stuff is pretty phenomenal. So thanks to them for making this possible for everyone to be able to hopefully get some statistical insights. So that said, let's jump right into it. We have 3 questions that I prepared for today. Again, I'm happy to take other questions as we move on. The first one here, this one's been a kind of interesting one because I've seen this pop up in a few different places. This is something that kind of somebody asks a question somewhere, then it kind of gets proliferated all across the various social medias and the like. And I think it's one of those examples of what is so frustrating about statistics, and that you have a problem or something that looks like a problem, and people come up with a bunch of explanations and an attempt to try to answer it. And a lot of people, they mean well. They're serious about trying to help, but a lot of the attempted answers are really kind of a post hoc rationalization in a sense, right? There's kind of this, people have a sense of what they expect to see, and so they try to come up with a reason why you should see it or why you shouldn't see it. But then the real problem is it's the actual expectation underlying the question is really where the problems arise. So much of statistics, and a lot of mathematics in general, is so counterintuitive to what we might expect that half the problem is asking the right question, setting the right expectation, and then understanding the answers therein. So the kind of high-level question here is you have a model with some kind of latent multivariate normal. So there's some kind of behavior you're modeling, and there's some kind of covariance structure, and you want to learn that covariance structure. Now, the kind of added layer on this is that this is going to be a high-dimensional problem. So we're talking about not a 3x3 multivariate normal. We're talking about like a 50 by 50 or 100 by 100 or 10,000 by 10,000, million by million, right? These really, really big covariance matrices. And the common recommendation for building a covariance matrix prior, when you want to learn a covariance structure, is use this LKJ prior, the Lewandowski, blanking on the middle name, I'm pretty sure it's 3 syllables, and it's like Kuroda. I think Lewandowski, Kuroda, and Joe. And this is a prior that was developed. So the original LKJ paper wasn't really about probability distributions over covariance matrices or anything like that. It was about unraveling covariance structure. And it just turns out that unraveling into the kind of intermediate terms that was done in the paper is very convenient for reparameterizing the space of covariance matrices into these relatively independent one-dimensional behaviors that you can then use to reconstruct the covariance structure back. In other words, it's a transformation from the constrained space of covariance matrices or correlation matrices to an unconstrained space and back. And so that was then the basis of the LKJ prior, where you're basically transforming to the unconstrained space, starting with a uniform or something that's slightly modified from a uniform, and then transforming back. And that's where that prior originally came from. I'm fairly confident it was all Ben Goodrich who put that all together. Now, the LKJ prior is not the only prior model that you might consider on a covariance structure. Before the LKJ prior model, the go-to was the Wishart model, the Wishart family of density functions, distribution, however you want to refer to it. And the big difference in the Wishart, or the inverse Wishart, is that it's parameterized by a baseline covariance matrix. It's not just a single parameter. You put in a central matrix structure, and the distribution will concentrate around that structure. The LKJ model, on the other hand, is a little bit different in that it concentrates around the identity matrix. There's no degree of freedom there. You can't put in some non-central, non-identity matrix to concentrate around. Now, there's other differences in the kind of multivariate correlations and the like, but one thing I want to emphasize from the beginning is that the LKJ prior model is by no means the only model. There's lots of models that existed before, and there's even more if you kind of dig into the more niche corners of the literature. Lots of different possibilities, and all of that presumes that you want to build a prior model directly over the space of covariance matrices. If you have a structured covariance matrix, if you're deriving a covariance matrix from some additional structure, then you're not building a prior model over the space of covariance matrices directly. You're building it over those intermediate pieces, and that can oftentimes be much more productive. We'll come back to that in just a second. So we have Wishart and Wishart. We have the LKJ. Like so much of Bayesian inference these days, people go to LKJ as a default. There's often not really any consideration of why one is choosing that over any of the others, which kind of falls into this issue of bad expectations. People are told it's a valid default, which means they don't have any responsibility for it. And then when there's some kind of unexpected behavior because they really didn't pay any attention to it, there's this frustration and there's this initial temptation to say the math is wrong. When the math was never wrong, it was your expectation coming into it that was flawed. And that's one of the big problems with default priors for any reason, or from any kind of motivation or principle or direction. But what is it about the LKJ in particular that's causing a problem here? So the challenge is if you start with an LKJ model, a high-dimensional space, and you simulate data from it, right? You do a prior check. You're doing better than assuming it's a default. You're actually looking into its consequences. You do a prior check, a prior predictive check, and you start looking at some of the covariance matrix structures that come out of this model. You start looking at some of the data that might be generated from those covariance matrix structures. And you start seeing behavior that is not quite what you're expecting or what you might want. And in this case, JD's asking about high correlations. When you sample from an LKJ model, I should do the show more here. You get most of the correlations you see are very, very small. It's very hard to get a sample where any of the off-diagonal elements of the covariance matrix, these pairwise correlations, are larger than 0.1, 0.01, and so on. And as we'll see in a little bit, that changes with dimension. It gets worse with higher and higher dimension. And so the question here is, well, what if you expect there to be some high correlations? Is the LKJ model wrong? Is there another prior model that's right? Should you expect those high correlations in the first place? And I think the big tension here is this discrepancy between expecting large pairwise correlations and what you see in high dimensions. So I want to spend a little bit of time talking about kind of trying to unravel what's going on with high dimensional covariance matrices, or spaces of high dimensional covariance matrices. and really kind of argue this isn't so much an LKJ problem. This is just a high dimension problem. Now, there's lots of ways of trying to intuit what's going on here. The space of covariance matrices, correlation matrices, more generally just positive definite matrices, is interesting in of itself. It's referred to mathematically as a cone, and the nomenclature comes from the fact that you can add two positive definite matrices together to get another positive definite matrix, but you can't subtract them. You can multiply two positive definite matrices together, but there's the inverses are not necessarily well defined, right? So it's kind of a limited algebra. You can add, but you can't subtract. You can multiply. There's a few other operations that you can perform. And that's what gives it the structure of a cone, right? It's kind of just like the positive, like you think of like R2, the two-dimensional real plane, and you just look at like the positive quadrant. That's kind of like a cone, right? And that you can add stuff, and it never kind of pushes you past the boundary. You're always staying within that boundary. You're always kind of moving away from that boundary as you add and multiply things. But the cone, I think, provides a really nice geometric intuition, where you have a point, then you have this kind of rounded but kind of increasing boundary, and then there's a cap on top. If you constrain the determinant of the matrices. So when you have like a space of correlation matrices, it's kind of like a capped cone, and then when it's covariance matrices, you have an uncapped cone that just keeps going forever. And that sets the stage for very, very conceptual intuition about concentration of measure. So in high dimensions, the kind of the general rule here is that probability distributions, things that look uniform naively, concentrate towards the boundaries. There's just a lot of volume around the boundaries, more volume in the boundaries than there is in the bulk, right? The example that I always go to is for Rn. As you keep adding more and more dimensions, you get more and more corners. And so if you have something like a cube, like a hypercube, you keep adding dimensions to, and then you put a sphere inside of that hypercube, and then you ask how much volume is inside the sphere, how much of the cube's volume is inside the sphere relative to outside the sphere, right? And that's a nice example because everything that's outside the sphere is those corners. And as you go into higher and higher dimensions, that ratio gets higher and higher. More and more of the volume is going into the corners, not in the bulk, not in that sphere, but in the corners of the cube. And that's a pretty generic phenomenon that you see. So in the cone case, what we'd expect to happen intuitively is that there'd be lots of volume on the boundary of the cone. What does that mean in terms of covariance matrices? Well, the boundary are singular matrices. So as we get closer and closer to the boundary, we get more and more singular. So naively, we expect as you go to higher and higher dimensions, more of the volume. So it's just a uniform distribution that's following where the volume is. All of that volume is going towards the boundary, not in the bulk, not around the identity matrix. So when you think of something that's uniform, it's not, flat around the identity matrix. It kind of almost looks like it's repelled away from the identity matrix. And again, it's not that it's being repelled, it's just that there's so much more volume away from the identity matrix around those boundaries at more singular behaviors. Another way of saying it is that as you go to higher and higher dimensions, singular behavior, or nearly singular behavior, becomes more and more typical. Non-singular behavior becomes very atypical. And that's really at the heart of this discrepancy, this tension between expecting large correlations and what you actually get with a lot of these covariance matrix distributions. So I have some code exercises that I'll show. The first thing I want to emphasize here is discuss a little bit about the pairwise correlations themselves and why they're kind of the wrong quantity to look at. So if you think about a high-dimensional multivariate normal, there's two classic operations, right? One is marginalization, one is conditioning. Now, marginalizing a multivariate normal is straightforward. If you want to remove, x dimensions, marginalize them out, then all you do is you eliminate the rows and columns from the covariance matrix. So, for example, if you have a 1,000 by 1,000 covariance matrix and you want to project that down to just 2 dimensions, you would remove all of the rows and columns except those that correspond to the 2 dimensions you're keeping. What's left? Well, you're going to have the 2 diagonal elements, and then you're going to have 2 off-diagonal elements, which, because of symmetry, will end up being the same. So we can really think about the off-diagonal elements of the covariance matrix, these pairwise correlations, as being low-dimensional behaviors. That are what happens when you marginalize from a high-dimensional space to a low-dimensional space. And because of that, they don't really characterize what's going on in the high dimensions. That's one of the reasons why this kind of counterintuitivity it starts to arise. If we want something that better represents the high-dimensional spaces, we want to think instead about conditioning. And so here, this is just my Gaussian process chapter. The reason I bring it up is I have the explicit formula for conditioning a multivariate normal. And so the way you condition is you partition your covariance matrix. And so let's say k pred is the dimensions you want to keep, that you want to look at, see what the conditional behavior is. K obs are the dimensions that you want to condition on. And then k mix are the off-diagonal blocks of the covariance matrix. The equation that we get out of it for the conditional multivariate normal is down here. Now, the key thing to notice is that it's not the pairwise correlations themselves that are influencing this. It's the inverse of that part of the block. It's not k-obs, it's k-obs inverse. Another way of saying this is that when we're thinking about high-dimensional behaviors, what's often more relevant is not the elements of the covariance matrix, it's the elements of the precision matrix. This is a subtle point, and it's one I don't fully intuit, but it shows up a lot in functional analysis, Gaussian processes, and so on. One of the kind of critical practical consequences of this is that when you talk about sparsity in a high-dimensional multivariate normal model, the relevant sparsity is usually not the sparsity of the covariance matrix, it's the sparsity of the precision matrix. Because it's the sparsity of the precision matrix that results in sparse operations. If you have a sparse covariance matrix and you invert it, you're in general not going to get a sparse precision matrix. And so even though things look like they're not dependent on each other, when you invert it, everything gets correlated. And then when you look at conditional behaviors, everything is conditionally dependent on everything else. Right? All you need is like one path through the variables. So even if dimensions, 1 and 3 aren't directly correlated, if 1 is correlated with 5, is correlated with 10, which is correlated with 1,000, which is correlated with 500, which is correlated with 3, when you invert the covariance matrix, you're going to get a connection between 1 and 3 because of that indirect correlation. And so when people talk about building these like sparse Gaussian process models, what you're effectively doing is constructing a sparse precision matrix directly. And there's lots of interesting mathematical ways of thinking about this. There's thinking about in terms of sparse or compact functional bases, where you're kind of modeling, you're decomposing functional behavior in terms of a basis of functions that you're adding together. But those functions that you're adding together have compact support, so they're local. They don't have this kind of global reach. That leads to sparse precision matrices, which you can then construct directly. You never have to invert this big, complex, high-dimensional object. Another place this occurs, if you think about the covariance matrices you get from Gaussian process covariance functions, the decay of the elements of that covariance matrix are determined by kind of the range of the correlations. The faster the off-diagonals decay, the less coupled far apart functional outputs are. For something like the exponential quadratic covariance function, they never decay fast enough. And so the correlation matrix stays dense, but more importantly, when you invert it, the precision matrix stays dense. Whereas if you have something like a Matern kernel with a sufficiently low number of degrees of freedom, there's enough of a decay of the covariance matrix elements as you move away from the diagonal that when you invert it, the precision matrix is extremely well approximated by a very sparse precision matrix. And again, that's where a lot of the speedups come from. So checking here. So JD's asking in the chat what the precision matrix is. Precision matrix is just the inverse of the covariance matrix. That's it. So mechanically, you take your covariance matrix, you invert it, that's your precision matrix. Statistically, there's a lot of information in the precision matrix that's easier to directly access than there is in the covariance matrix. And that's kind of what I'm trying to get at here. So a lot of the conditional dependencies are really encoded in the precision matrix, not the covariance matrix. And it's really just because of equations like this. So that's one thing to keep in mind, is that if your intuition is about these covariance matrix elements, but the covariance matrix elements aren't actually capturing anything about what's happening in high dimensions, well, your intuition might be misdirected because you're looking in the wrong place. That's one thing to kind of identify here as a potential point of confusion. All right. So let's look at the code, which I realize I didn't set up an OBS yet, so apologies. Just give me a second here. Make sure I have... Okay, so that. Okay. And then I need to bring on a new window for this. Okay, here we go. Oops. And let's just make this a little bit smaller. And a little bit smaller. Okay. Boom. All right, so what I've done here, I just covered myself. Okay. Let's get serious. Statistics. What I've done here is I've just simulated from an LKJ prior. So we're looking at correlation matrices here, not covariance matrices. The determinant is fixed to 1. And I've done it under 3 scenarios. I've set the parameter in the LKJ model to 1, the square root of the number of dimensions, which is often presented as a heuristic, kind of back of the envelope default for how to configure the LKJ as you go higher dimensions. I set it to the number of dimensions directly, and then I set it to the exponential of the number of dimensions. Now that parameter, keep in mind, determines how much the LKJ model concentrates around the identity. The larger eta is, the more of a concentration you have. If eta is 1, then you have a uniform distribution over all covariance matrix or correlation matrices. If it's less than 1, you actually get repulsion away from the identity matrix. And then what we're looking at here, so this is for eta 1. And then I simulated 5 dimensions. Let's just see here. 5 dimensions, 10 dimensions, 50, 100, and 500. That's what the colors are. So as it gets lighter and lighter, we're going to higher and higher dimensions. And then the 4 quantities we're going to look at are the log determinant, the average off-diagonal element. So you take the covariance matrix, you just look at the off-diagonal elements, and then you average their values, as well as the minimum and the maximum off-diagonal value. So we're getting a sense for kind of what the off-diagonal elements are looking like here, right? What's their average, and then what are the tails? So for eta equals 1, remember this is the uniform distribution over correlation matrices. What do we see? So the first thing that we see is that as we go from 5 to 10 to 50 to 100 to 500 dimensions, let me double check that wasn't changed. Looks like it was it. I'm just looking at the plots here. I think the plots might just be up to 500 or up to 100, not include 500. It's the same pattern continues. I just want to make sure I'm getting things right. Anyways, so when we have a 5-dimensional space and we sample correlation matrices from the LKJ prior model, the log determinant is pretty large. It's pretty close to 0. The largest it can be is 1, and the smallest it can be is 0. The determinant is between 0 and 1 for a correlation matrix. And you take the log of it, it's between minus infinity and 0. And the smaller it is, the closer... the smaller the log determinant is, the closer the determinant is to 0, the more singular the matrix is. And as our kind of intuition suggested, as we go in higher and higher dimensions, we're getting more and more singular matrices. There's just more volume around this boundary of nearly singular correlation matrices. And that corresponds to the log determinant getting smaller and smaller, right? This is the whole distribution here, right? So it's not just that, like, there's a tail of more singular correlation matrices that we're getting. Almost all of the correlation matrices that you're simulating are near that boundary, right? The tail that exists is the tail that remains towards these very non-singular correlation matrices. Those become very, very atypical as we move to higher and higher dimensions. And again, this is the uniform distribution. There's nothing about the LKJ model that's repelling away from the identity. This is just the geometry of the space of correlation matrices that's doing this. Now, if you look at the average off-diagonal element, you'll see that as we go in higher and higher dimensions, the average elements are getting smaller and smaller and smaller. We're getting smaller pairwise correlations off the diagonal. And it's not just the average, right? The average might be that there's kind of symmetry. Things get more symmetric as you go to higher and higher dimensions. But no, it's actually worse than that. The minimum is getting smaller and smaller, and the maximum is getting smaller and smaller. In other words, we're getting these pairwise correlation coefficients are getting squeezed towards 0 as we go into higher and higher dimensional spaces, which is what people were seeing. People were seeing that these LKJ prior realizations never had these large correlations that they were expecting. Now, the mathematical reason for this is pretty straightforward. As you get to larger and larger matrices, every time you invert something, every time you take a determinant of something, you have more and more stuff that's contributing. More and more stuff is adding together. And if any of that stuff is large, even if it's just a few, because you're in a high dimensional space, there's enough opportunity for those exceptional large things to add together and make things look more singular. And so two things are happening, right? You're getting this kind of shrinkage of the off-diagonal elements, and yet, even with that shrinkage, you're still getting more and more singular behaviors. So what if we change eta? If eta is larger than 1, we should get concentration around the identity matrix. Can we fight this? Yes, to a degree. So in this plot, I've set eta to the square root of the number of dimensions. So as we go to higher dimensional space, we concentrate even tighter around the identity matrix to fight against this growing volume near the boundaries, right? But it's a relatively moderate increase of regularization, just the square root. It's a very slowly growing function. So the behavior we see isn't quite as bad as what we had before, but it's the same basic pattern. Things are getting more singular. The off-diagonal elements are squeezing towards 0. All right, so square root, that's a little bit too conservative. Let's go higher. Okay, so let's just use the number of dimensions. Again, things are getting better, right? We're not getting out to minus 500 log determinants or minus 400. We're now at minus 100. There's a lot of regularizations happening here now. But we're still getting pretty strong squeezing of the off-diagonal elements. And then if we go to the exponential of the number of dimensions, so now if the dimension is 500, our eta parameter is the exponential of 500, which is getting very close to the maximum floating point, double precision floating point number you can represent. In this case, things stay very non-singular, right? No matter what dimension we have, the log determinant is staying pretty close to 1. That's great. But we're still getting pretty strong squeezing of the off-diagonal elements, right? And this is this tension. Whether the matrix is kind of nearly singular or just kind of nearly singular or pretty close to the identity, because there's so many off-diagonal elements, if any of them are non-trivially large, then they're going to add up and completely overwhelm everything and cause super non-singular behavior. So even to have slightly non-singular behavior, even to be just a little bit away from the identity matrix, all of your off-diagonal elements have to be pretty small. That's just a consequence of being in a high-dimensional space. So let's step back and review. What we're seeing here with this LKJ model is that as we go to higher and higher dimensions, even with increasingly strong regularization, we're getting correlation matrices with very small off-diagonal elements. And this is not a problem of the LKJ model. This is an inherent property of the space of positive definite matrices with a unit determinant. In other words, the space of correlation matrices. When we think of large pairwise correlation coefficients, that is a fundamentally low-dimensional behavior. As we go to higher dimensions, it becomes less and less typical. Right? Just think of the canonical concentration measure example. In one dimension for a normal, most of the samples you draw are going to be near the mode, near the peak of that distribution. But as you go to higher and higher dimensions, even if you have an IID normal, you still have this peak, but now all of your samples are concentrating in the surface around the mode. And the problem is, with all of these new dimensions, there's just so many opportunities to stray away. To move away from that low-dimensional behavior. There's that low-dimensional behavior that you're expecting, that you're familiar with, that you can interpret, intuit, is atypical in high dimensions, right? That's why high-dimensional spaces are so weirdly confounding. They're so counterintuitive, because the things that we've become used to become atypical, become unrepresentative of what's happening in the higher dimensional space. So, I think there's two kind of productive resolutions to this problem. Maybe three. One is just to say, it is what it is. This is what happens in high-dimensional spaces. I need to change my expectations. And once you change your expectations, things look a little more reasonable. In that guise, you might then focus instead on the values of the off-diagonal elements. Look at things like your prior predictive data. Does that look reasonable? The elements of the precision matrix might be a better thing to look at than the elements of the covariance matrix, and so on. Right? Those kind of capture behaviors that are probably much more important to the kind of quantitative outputs of interest rather than the pairwise correlation coefficients. Another possibility is to say, no, I actually do want large pairwise correlation coefficient. Forget typicality in high dimensional spaces. I want there to be a large off-diagonal element in my covariance matrix. I don't think this is necessarily a productive thing to do, but if that's what you want to do, then the problem there is you haven't really defined a model. Okay, great. You want one of your correlation coefficients to be large. Which one? Can any of them be large? Can a certain subset of them be large? What patterns of large values are acceptable? Can they all be large? What can 10% of them be large? Is it a spectrum where there's a lot of large values, even more medium values, and then very few small values? Is it that they're mostly small and every now and then there's a very large value? Right? Like, all of these things correspond to different models, and they have different consequences. You could try to, say, put down a heavy-tailed hierarchical, like an exchangeable heavy-tailed model on the off-diagonal elements, so that most of them are very small, and then every now and then one gets to be pretty large. You still have to kind of figure out the proportion of them that you want, but I'm going to guess that if you were to implement that model, which isn't too difficult, especially if you're just looking at prior consequences, and you looked at those prior consequences, I don't think you're going to like what you see. Because, again, that kind of behavior causes weird havoc, chaos in high dimensions. It doesn't do what you think it's going to do, or what you may think it's going to do. I think another way of saying it geometrically is that if there is this low-dimensional behavior that you want, you have to define what all of the possible low-dimensional behaviors are, and then you need to build a model that concentrates around the range of possible low-dimensional behaviors. You can't just say one. You have to categorize all of them, right? Enumerate all of the possible low-dimensional behaviors. What is this low-dimensional submanifold in the space of correlation matrices that you want, and then build a prior model that concentrates around that. And that is an extremely difficult problem, often because those kind of low-dimensional submanifolds are wild. They're just nasty, nasty geometry. The most productive way of trying to tackle that is not to try to directly encode the low-dimensional behavior, but rather to derive it. So, and this is where we have to move away from building a model directly over correlation matrices, and instead deriving correlation matrices from structure. So, let's So the classic example of this is that if I write something like, instead of, theta I, I'll write this. Let's do it. So I'm going to do that for a matrix. Hopefully that's understandable. And we'll make this a multinormal. Right, so that's going to be the kind of model that we don't want to build directly, because we don't know what kind of prior to put over the space of correlation matrices. So what can we do? Well, as I said before, one thing that we can do is, instead of modeling sigma, we could try to model lambda, which is the inverse of sigma. Right, this is what a lot of functional models do. But what's often more useful, more productive, is instead not really model theta directly at all. Instead, do something like, theta I is alpha plus alpha 1 ji, right, something like this. And then if we put a prior model or a probabilistic model on alpha 1, let's make this bold. Nah, let's do this. Right, something like that. This model induces, right, there's a push forward model for theta. And thetas that share common factors will be more correlated than theta components that don't. And so this gets into the kind of quote unquote random effects model, factor model, however you want to interpret it. But a lot of those models, if all of these alphas are normals, then this manipulation here turns out to always define a multivariate normal. And the structure of the covariance of that induced, of that derived multivariate normal is determined by, you know, the sharing of the alphas amongst all of the theta I components. This is basically where things like ANOVA come from, right? Where your these like classical random effects models, you're trying to decompose some behavior into these component pieces, but what you're often doing analytically is decomposing a multivariate normal into component pieces. Right, analysis of variance is literally trying to understand the kind of the covariation of all of these pieces, which under certain assumptions can be characterized with a multivariate normal as well. And then, so for example, if you have like a block of components that you think are likely to be more strongly correlated with each other than any other component, you can try to impose a block structure on your covariance matrix, or you can say that there's a block of pairwise correlation coefficients that can be larger than others. That can be done directly on the space of correlation matrices, but can also be induced by adding a term for a common term for all of the components in that block, and then deriving this induced multivariate normal. And so when you start thinking about things like, you know, there really is this low-dimensional structure, or there's certain kind of encodings that we want to force, then it's often easier to think in terms of this direction. And you could have nonlinearities. You can make this more complicated, but I think this is going to be a more productive route than trying to work something like the LKJ directly. Right? The LKJ is when you say, I don't really know anything about the individual components. I just know that I want there to be some mild concentration around the identity matrix. If you know more than that, if you know there are these very atypical low-dimensional structures that you want to emphasize, then you're going to need to build a model that very intentionally emphasizes those atypical behaviors and the fights against the rise of volume near these singular boundaries. That's often very difficult to do with a monolithic model directly. Might be able to get away with something like an inverse V-chart or a V-chart, something like that. But often it's not, because the problem is it's not like a geometrically, if there's a single matrix that has the right structure and then you want to add a little bit of perturbation around that. It's likely going to be that there's like a surface of correlation matrices that are all valid, that have the right representations or manifestations of that low-dimensional behavior. And that's going to be very difficult to try to parameterize directly. And that's where models like this can be much more effective. So to kind of sort of answer your question, I know this has been kind of a long roundabout discussion here. where are we? Uh, if I thought that there were something like genre being relevant, then to me that's kind of like block structure in the correlation matrix. But instead of trying to construct that directly, I would think more of this kind of random effects like model, um, and go in that direction where it's like there's the kind of baseline behavior, there's the behavior for the kind of correction from the baseline for all of the movies in one genre, there's a correction for all the movies in another genre, and so on, and then go down that line, thinking more in terms of factor heterogeneity than anything else. Right, and again, the LKJ is more for that more ignorant circumstance where you don't have any information like that. You don't have any structural information, and you're just trying to get some basic regularization to avoid singular behavior. So Albino Monkey 99 is asking in the chat, in the movie case study, the alpha are something like the latent features, factors of the movies. Yeah. So that's where you start moving in. So the thing with the movie case study is that I kind of treated each individual movie as its own monolithic thing. There were no properties or descriptions of the movies. Same with the Raiders. And so when you start saying something like, well, I think there's because of that, they're all exchangeable, right? There's nothing that differentiates one movie from another. I know they're different, but I don't know anything that might cluster or group them together. And that's why the LKJ prior model is a really nice choice for that. If I knew something about the properties of the movies or even the properties of the Raiders, then that changes the scenario because now there's more information. That might then motivate looking at things like genre, looking at structured covariance matrices, and instead of trying to model them directly, instead of trying to derive them by looking at these kind of additive corrections to capture the systematic heterogeneity instead of trying to force it with a covariance matrix. So let me know if that kind of roughly answered the question. This is a subtle point, right? There's a lot of complication here, and this is one of the dangers of probabilistic programming is that it's very easy to shoot yourself in the foot, and right, it makes it very easy to do very complicated things. I mean, this is really true of any black box. It's not just probabilistic programming. It's when you use defaults without really digging into understanding them, it's easy to make mistakes. And a lot of things in statistics are unfortunately just very difficult to dig into and understand. That's just the frickin' reality of stuff. And so there's this frustrating loop people get into. And I want to make very clear, I'm not talking about JD here who asked this question. It's kind of more ranting about others. That people will kind of look into a topic very superficially and realize it's complicated and go, nope, not for me. Don't need to worry about that. Going to find some reason to rationalize away, and then they'll go to a default. And then that might work okay for a while, but eventually they'll come into a problem and then realize, oh no, that thing that I ignore was actually a problem this whole time, but I don't want to deal with it, right? The term I've like to use here is conceptual debt, right? Ignoring this stuff is a conceptual debt you're going to have to pay back later, eventually. And unfortunately, it just means that there's a lot of work you have to do initially when you're digging into some of these more subtle subjects. Or you have to, and at the very least, you have to understand, like in the LKJ case, maybe you don't understand the geometry of correlation matrices, but you do at least want to understand the basic assumptions that the LKJ model is making and what assumptions it's not, right? That small correlation coefficients are kind of the standard in high-dimensional spaces. The LKJ model isn't trying to fight that. Even with very, very strong increasing regularization, it doesn't really do much to fight that. That's just a reality in high-dimensional spaces. If you want something else, LKJ prior model is not right for you. That's okay. That's okay for that to be the conversation, and then you'll try to find something that's better. Okay, so, yeah, so JD's asked some questions here in the chat. The random effects type model dispenses with the large correlation matrix and prior on it, correct? Yes. You don't explicitly parameterize the correlation or covariance matrix with a multivariate normal. Instead, you derive it. So you might have another multivariate normal on those alphas. Or it could be a hierarchical model. You can have all kinds of different assumptions there. But you don't explicitly build the multivariate normal. You build all of this latent structure, and then when you derive and calculate what the thetas are, that's implicitly constructing, some kind of correlated model for all of the thetas. And in some cases, you can do that convolution analytically and show that it's a multivariate normal and show what the induced model is. In some cases, you can't. So the nice thing about another nice thing about going in that direction is that you can make it arbitrarily complicated. It doesn't have to end up in a multivariate normal. It can be some other more complicated model, but you can still implement it directly. There's also tying here to structural equation modeling, SEM, which in most cases is really just you write down all of these arrows, and it's really just specifying a structure of a covariance matrix. That's another way of kind of thinking about deriving the structure as opposed to specifying it directly. Yeah, so there the other priors, the Wishart and inverse Wishart, those were the classic examples. LKJ is pretty new. For decades, especially in the Bayesian world, the Wishart and inverse Wishart were the go-to. They're the conjugate priors for the multivariate normal, so you can do a lot of analytic calculations there. Which is why they were so popular. But the LKJ just has, in terms of kind of a relatively non-informative prior model and correlation matrices, LKJ has some nicer properties. I think it's pretty exceptional to have a circumstance where you want a correlation matrix model that concentrates around a non-identity matrix. It can absolutely happen, but it's relatively exceptional, I think. So what I think the trigger here is if you ever hear about a model where you want to concentrate on a particular matrix structure, right, where in a particular like baseline matrix, values for all of the elements, that's where you go think about Wishart, inverse Wishart. And then inverse Wishart's kind of like the inverse gamma to the gamma. It's more heavy-tailed than the Wishart is. Although heavy tails and high dimensions get weird, so don't take that analogy too far. And then there are others out there. I'm by no means an expert in all of them. There's some wild stuff out in the literature. There's some cool matrix linear algebra that you can do in a lot of cases. There's a lot of interesting math out there. I don't know how productive or practical any of that stuff is, but there is stuff out there, and there could be some really cool practical applications that are waiting to be dug out. That just haven't yet. Is there an example of the kind of deriving a multivariate normal that you, in lieu of starting with a multivariate normal in Sandcode? Not directly. The problem is a lot of the examples kind of get, I don't want to say it. They kind of get black boxed. And it's like, here's a technique. We're going to look at it in isolation, and we're not going to compare it to something like a multivariate normal. What I would recommend doing is looking at a multivariate normal model and looking at data summaries, statistics that you think capture a lot of the kind of interesting structure. So look at things like empirical covariations, empirical correlation coefficients, and so on. And then build up a model with, these kind of factor contributions. Simulate, and then construct those summaries. And then do the same thing for a multivariate normal, we'll say an LKJ covariance matrix. And just see what kind of different structures you get there, right? Like that would be kind of the way to start building some intuition about what's going on there. You no longer have an explicit, say, like correlation coefficient to compare, but you can look at the summaries of the data that might manifest some of those behaviors. And that's like, if I were trying to dig into this, that's what I would do. I'd start with a simple example, maybe have like one or two factors, even just one factor, which should give you kind of something like a block structure of the induced covariance structure, and see if you can resolve that block structure in something like the empirical covariations and so on. That would be what I would recommend. I'm sure there's stuff out there. It's just like, if you dig into the old ANOVA and random effects literature, it's a lot of weird language to dig through. And I know it's out there, but it's often presented in a way that they're not talking about the models. The models are always implicit. They're talking about the estimators and the estimator distributions and things like that. And so it can be very kind of tricky to dig into the literature and find these direct comparisons. That said, if anyone in the chat or reading after the fact knows of an example that they think is useful, feel free to drop it for JD to take a look at. All right, so I think we covered that one pretty well. A nice excuse to talk about high dimensions and counterintuitive statistical behaviors and the terror of defaults and black boxes and all of that lovely stuff. Speaking of terrors, we now have our next question. So Zach is asking about SUTVA, which is one of these causal inference acronyms. And so I thought for here we would just kind of play around with some equations on the blackboard. And by blackboard I mean the text file. So in the kind of causal inference that Zach's kind of alluding to here, the goal of interest is pretty much always this average treatment effect. And so a simple way of thinking about average treatment effects is, like what's the model that is being assumed there? So let's say that we have two observations. There's y1, and say there's a mu1 and a sigma, and then there's y2. Right? And these two observations correspond to two groups, control treatment, just two things, two distinct circumstances where we think there is a systematic difference. Not only do we think there's a systematic difference, we think that that systematic difference is going to generalize to other circumstances. Right? That's where one of the reasons I get very frustrated with a lot of the classic causal inference literature is that it's confounding two different things. What matters for actual causality and kind of what people are actually interested in practice is understanding what patterns, what behaviors generalize from one circumstance to another. What a lot of the classic causal inference literature does is it makes a bunch of assumptions about certain patterns, relatively simple patterns that can be quantified with simple estimators, and says, well, under those assumptions, this will generalize, so just calculate that thing. And there's not a lot of discussion of what happens when that stuff doesn't hold, right? It's always just like manipulate whatever you have into that simple circumstance so we can use those results. So in this case, if we're assuming that the difference of behaviors in these two circumstances is systematic and will carry over, then what we're interested in is the difference between mu1 and mu2, right? And ideally, we look at, say, like the joint distribution of mu1 and mu2, because that would let us do all kinds of interesting things. But in the kind of classic causal inference literature, what you're going to see is something like this, where it's like, well, it's really just the difference. You want to know the sign. Is this greater than 0? Is this less than 0? So on. Do things get larger? Do they get smaller? Or do they stay the same? Now, we don't know what mu2 and mu1 are, but we can think of estimating them. So we have an estimate for mu2, which is just y1. And we have an estimate for mu1, which is just... Get those right. And so then mu2 minus mu1 is just hat mu2 minus hat mu1, and really I should say It's approximately that difference, which is just y2 minus y1, right? And so this is the quote-unquote average treatment effect. If we assume that, say, 2 is the treatment circumstance and 1 is the control circumstance, then the difference in those observations, difference in those estimators, I should say, is the effect of the treatment. Now, this is loaded, right? Effect here is this linear change. It's not the joint behavior. And it's assuming that that's not only is that that difference that you're quantifying is a difference, you're assuming that the difference generalizes other circumstances. And that is an assumption you have to make. There's no estimator that will prove that behavior will actually generalize, right? The term causal identification is not identifying things that are causal. It's not identifying things that generalize. There's no mathematical way to quantify what behaviors are persistent across circumstances unless you have data across those different circumstances. If you only have data in one circumstance, only way to make predictions with other circumstances is to assume what generalizes and what doesn't. The identification is all about, is there some difference that you can observe, right? And what gets so confusing to me, and I think what confuses a lot of others, is that causal identification is kind of presented in terms of these estimators, and what estimator differences are informed by the data. But what really you care about are things like the differences of parameters or the joint model of two parameters, right? Now, this might sound pretty trivial in this simple case, but as we get to things like Sattva and Zach's example, then it becomes a lot more important. Now, a more realistic example is that you don't just have one observation in each group. You have, a bunch. So let's say we have n observations in each group, right? But we're assuming, again, it's kind of systematically homogeneous in those two groups. So now, our estimators are not just y1 and y2, right? It's 1 over n, sum over n, y2n, and so on. This is where the average and average treatment effect comes from, is that for 99.99% of the classic causal inference literature, you're looking at two groups. One group has kind of been treated in the same way. One group has been treated in another same way. And you want to look at the difference of those groups, assuming that it manifests the same in all the individuals. And then it's the same calculation. What we care about is the difference. What we're going to calculate is the difference of the two parameters, which we can estimate as the difference of the two estimators, which is just going to be something like that, right? So that's like your classic average treatment effect model. And what we're effectively assuming, again, we're assuming that there is some pattern that's going to generalize, that's going to be persistent. And then we assume that that pattern manifests in the centrality of the data, so that the average of the data estimates that persistent behavior. We can look at the difference in persistent behaviors across the two groups, and this will be the thing that allows us to make predictions about the differences that will occur in groups going forwards, right? Very, very simple assumptions. Very strong assumptions. But they can be very difficult to understand, especially if you don't recognize that there's just like these modeling assumptions that are being made underneath it all. So now what happens when we get to Zach's example? So in Zach's example, we don't have these independent observations for a bunch of individuals. Instead, we have, let's say we have an individual, or I individuals, and each individual is in a market. Now, there's a finite quantity of things that can be purchased. And let's assume that there's enough demand that everything that's available is going to be purchased. And that means that every individual doesn't get to buy whatever they want. So that if Y is like the purchasing of a given individual, they're not going to purchase based on their demand. They're going to purchase based on the demand and the availability. And so one way of thinking about the model here is that the model, the joint observational model, for all of the observed purchases, we can think about it something like, well, there's two things. There's the total purchase, and then there's the proportion of purchases. Let's look here at the proportion of purchases, because it will factor things out. This might be something like a Dirichlet. Let's say it's continuous purchasing. We'll ignore discretization. Right, so we might have like a Dirichlet observational model. And then if there was uncertainty in the total amount, we could use something like a, I don't know, like a log normal for the total amount, and then a Dirichlet for how the total amount gets distributed across the individuals. That's kind of the classic way to model a distributional observation like this. Now, one problem with the Dirichlet is these parameters are not the most interpretable. What I like to do with my Dirichlets is write alpha I as rho I divided by tau plus 1. Why do I do that? Well, when you do that, the corresponding Dirichlet turns into a model that concentrates around a simplex given by the rho i's. So now you get this really nice classical interpretation, like classical behavior for a probabilistic model. We have a baseline simplex rho I, and the observed proportions of sales will concentrate around rho I. They'll scatter around rho I, right? Just like the data up here will scatter around mu1 and scatter around mu2. It's just now happening in a higher, not only a higher dimensional space, but a higher dimensional constrained space, because it's a simplex. I love this thing. Love it to death. I've used it so often in the past 2 years. It's great. And so like the rows are something we can interpret. We put a prior model on it. Tau quantifies how singular the distribution is, right? It's basically your measure of variability. The smaller tau is, the more concentrated the Dirichlet model is around rho. The larger tau is, the more diffuse it is. And this does restrict the Dirichlet a little bit. So the standard Dirichlet, the alphas can be less than 1. And when the alphas are less than 1, then you get kind of a repulsion away from any point in the interior towards the boundaries. So by adding this plus 1 here, we're eliminating all of those configurations, which is fine in most cases. Usually you don't want that kind of repulsion. But if you did want that repulsion, you then want to work with the alphas directly. But this, love it. It's my favorite. So, what this allows us to do, right, is model, is up here, right, our full parameter space is mu1, mu2, and sigma. Down here, our full parameter space, up here, our parameter space was mu1, mu2, and sigma, and then we made the assumption that the relevant behavior that persists, maybe it's not mu1 by itself, maybe it's not mu2 by itself, but the difference of mu2 minus mu1, that's the thing that's going to persist going forwards. And so we want to learn that behavior, right? That is the key assumption that goes into something like an average treatment effect analysis. In Zach's example, we have all of these observations that are correlated with each other. And there's all of these alpha parameters. So now, if you want to think, causally, not classically, just like from a modeling perspective, what behaviors persist, you have all of these alpha parameters that are hard to interpret on their own. And then the question is, which where does the pattern manifest? So say that like the first half of these buyers are treated in some way, and the second half are treated in another way. So it's a controlled treatment, two treatments, however you want to think about it. So that there's actually kind of a separation. There's like alpha 1 to alpha I over 2. And there's alpha I over 2 plus 1, alpha I, right? Something like that. And now I've got these two groups. Half have these alphas, the other half these other alphas. What am I comparing? What is the thing that the pattern that actually persists? That's the fundamental problem here. So you'll look at this, and somebody will say like, "Oh, well, subfa doesn't hold," or there's a spillover, or influence, or interference, or these other terms, right? What does any of that mean? That only means something in the context of an explicit data generating process. A lot of times what people use these acronyms for is to say, well, the standard, this example is not a good model anymore. Great. Yes, that can be useful in identifying when a certain kind of default analysis or black box is inappropriate. But if you want to do something in those cases, what do? Right? You can't just say, well, Sattva, so I can't do anything. That's garbage. Of course you could do something. You just need a more complicated data generating process. And then you think more carefully about where the persistent behaviors are. So from kind of pure mathematical perspective, from a modeling perspective, I should say, if we write the Dirichlet like this, think about what the right data generating process is the proportion of sales. We have the parameters, the alphas across the two groups, the one treatment group and the one control group, and we have to then ask, well, okay, what is the difference? What is the actual meaningful variation between alpha 1 to alpha I over 2 and alpha I over 2 plus 1 to alpha I, right? And now it's a multivariate problem, right? What's a multivariate difference that matters? Is it a subtraction 1 by 1? That doesn't make any sense. Do we take an average and then subtract? What does it mean take an average of the alphas, right? This stuff just gets weird, right? But if we reparameterize the alphas in terms of these rows, now it's a little bit better, right? Because now we can think about actual probabilities. And so now the question is, and then the nice thing about simplices is that splitting it gives us another set of simplices, right? So if we renormalize, something like this, we'll get these two subsimplices. We'll call it row 1 and row 2, right? So now we're in a slightly better position because we can now ask things like, okay, I've got these two groups. The behavior in those two groups is characterized by these two simplices. What is the relevant measure of difference between those two simplices? And you can bring a bunch of just abstract math on this. You can say like, okay, well, there's a lot of ways of measuring distances on a simplex. A lot of ways of trying to quantify a difference between two simplices. Or maybe it's not a difference at all. Maybe there's some other more meaningful quantity that really gets at what you care about. Maybe it's, is what actually matters here what any individual is doing, or is it this normalization itself, right? What you actually care about is this? where it's like the total relative demand in group 2 versus group 1? Is that the thing that will persist? Not what any individual is doing, but when you split the market and you say like you advertise to one group, does that mean that their demand just goes up relative to the other group? That would capture that. So I think from a causal, when you actually get into the relevant causal question here, and causal's so hard because I don't want to. There's like the causal inference literature, and then there's actual causality and physical causality and kind of meaningful causal predictions and generalizable predictions and hypotheticals and things like that, right? If from a non-causal inference literature perspective, what you care about is identifying that persistent behavior and then learning that persistent behavior. When you have a multi-dimensional output, the real hard part in all of this isn't the estimation, it's identifying what the persistent behavior is. Then you can infer that behavior directly. Another interesting thing that happens here is that this difference here might be very difficult to estimate directly with averages of the y's, right? You can kind of do it. It'll probably be very nonlinear. But from a Bayesian inference perspective, you don't need to do that. You just build your model, and then you look at the induced distribution of the sum of the rows in one group versus the sum of the rows in the other group. And then another way of approaching this, not unlike some of the discussion that we just had, is that instead of modeling rho directly, you can derive rho from a softmax model, right? So you can have something like rho I, or rho 1 to rho I is softmax. Let's call it, sure, we'll call it mu. Mu1 to mu I. For Patreon supporters who have seen the discrete choice chapter, we might know that this has to turn into something like nu, say like 0 differences, because will be non-identified otherwise. And then one can derive these nus from something like like a random effects like model. Or something like that, right? And then one can say, okay, so what actually matters is that the alpha 1 here is, this will be like the alpha 1 that corresponds to a certain subgroup of the groups, right? There's some demographic that's more susceptible to the advertising, or there's an income bracket that's more willing to purchase your product, or whatever it might be. That's the pattern of interest. It's not the monolithic behavior. You have to decompose the behavior of the two groups into these contributing behaviors. One of those contributing behaviors is the one that you think is actually susceptible to this treatment, and you think that treatment effect will generalize. So you go through all of this, and then what actually is your kind of causal question is something like this, right? It can be that precise, that refined. Having an interpretable probabilistic model that's capturing an explicit data generating process that only allows you to incorporate all of the constraints, all of the structure of the problem. It allows you to identify these very nuanced contributing behaviors, these individual pieces. And you can start making these very nuanced, quote-unquote, causal claims about what behaviors will persist. Where do you think the treatment is actually having an impact? And if that impact were to persist, what would it look like if other things changed, right? The fun thing about this is that you can leave this fixed and allow the other alphas to change. to account for things like different demographics coming into the groups, expanding to other demographics, and so on. What happens when you have a new product? Maybe this alpha is the same for the new product as it was for the old product, but a bunch of other contributing behaviors change. I think just so much more straightforward to have a probabilistic model already built. And then instead of trying to ask, well, what's my causal effect? What is my average treatment effect measure? You instead step back and say, okay, what is the difference or variation of the parameters that is capturing some persistent behavior? From a Bayesian inference perspective, you just learn you fit the joint model, you can learn that difference, and then you can incorporate that difference into predictions, decisions, and everything going forwards. There's no SUTFA, there's no spillover. Everything is approached in the same exact way. All right, I got some questions here in the chat. All right, so George is asking about power of HMC, but lack the understanding of physical mechanisms behind it. Where should I start? All right, so this is slightly off topic. Let me finish answering this question here. I'll come back to that because it's somewhat short, and then we'll get to our last question. All right, so just to conclude here, Zach, I hope this answered the question. I know this isn't the kind of like standard, like I'm not answering it using the language you used to ask the question, but it's because I don't like that language and I want it to stop. But it's also because this is how it actually approaches the problem, and I think this really is where the more productive approach is, right? You're probably already thinking about a lot of these things, and what I find a lot when people come to me with questions about a lot of this classic causal inference stuff is that they know a lot, but they don't know how to rectify that knowledge with the tools available to them. And that's what causes this frustration, right? It's like, well, yeah, I know this thing should be different, but I don't know how to write that as an average treatment effect. And so I don't know how to get this published in a causal inference journal, et cetera, right? And the problem is trying to force a square peg into a round hole. The beauty of probabilistic modeling and Bayesian inference is that everything is just part of the modeling problem. You've modeled the data generating process for group 1 and group 2. You've built a joint model of those two data generating processes. You can learn the joint behavior and then directly incorporate all of that coherently. You can look at differences. You can look at proportional changes. Whatever you think is actually capturing this relevant behavior. You model that directly, you learn that directly, and then you can incorporate that into your inferences and decisions. And it doesn't matter if your observations are IID, it doesn't matter if your observations are correlated, it doesn't matter if the differences you're looking at are on a simplex or in high-dimensional real numbers, or you're looking at differences of correlation matrices, right? You can imagine tying this into the previous question, and what actually matters is that there's some correlations that are influenced by a treatment, right? Imagine something like that, where it's like, the treatment isn't necessarily changing the baseline behaviors, but it's causing a group of people to be more correlated than they would be otherwise. That would be a fun thing. I don't know where that would show up, but I can imagine that showing up in like a psychology or sociology kind of analysis. And that's something that's not easy from probabilistic modeling perspective, but straightforward, right? Again, you have a process you follow, and that process allows you to incorporate all of this domain expertise in a very beautiful, elegant way. I love it so much. And I think that just finally to note, I think the thing that frustrates me most of all about a lot of this causal stuff, the zeitgeist, is that it's kind of trivial. Right, from a probabilistic modeling perspective, we presented it here. It's not that different from how you would tackle any other part of the modeling problem, right? It's a treatment and control group. It's just two different data generating processes. Cool. We're going to use our same modeling strategies. It's using Bayesian inference all at once. We don't have to change how we estimate anything. You know, if the thing that you care about, the difference that you think is capturing this persistent behavior, if that is not actually informed by the data, then you'll see it, right? What's going to happen? Well, your posterior for that, then your marginal posterior for that behavior is going to get super wide. So you're never going to get burned by throwing out some estimator that's horribly well behaved because there's some assumption that you had to make that you didn't know how to make. It's just the best, right? It's hard to argue against the zeitgeist. It's hard to argue against the status quo. But I cannot emphasize how much more straightforward a lot of these problems are if you just think about it from a modeling perspective. Drop all the acronyms, drop all of the defaults, ask what your data generating processes are, build a joint model of all the data generating processes at the same time, do Bayesian inference all at once, and then use whatever you like going forwards. Or, pick out the pieces of that you want to use to inform your predictions, your decisions, your inferences, and the like. So hopefully this was a sufficiently compelling example. This is, one way of approaching it. Depending on your precise problem, might be other ways. But I do think in a lot of these kind of saturating markets, something like a durational observation model is a pretty useful way of approaching it. There's some bells and whistles you could add. Again, you could have something like a model for the overall demand and then the proportion of that demand. And that would allow you to split up things like changes in relative demand. Does one group become more interested relative to another group versus changes in the overall demand, right? That's even better because now you have parameters that model the overall amount. You have parameters that model the relative proportions. And you can then ask which of those parameters are going to be influenced by the treatment. Maybe it's both. Maybe it's just one. Right? It's just, I don't know. It's fun, right? It's exciting. I don't know. I'm getting excited about this stuff because there's so many cool possibilities, and it's all just so straightforward. But you have to come at it from this probabilistic modeling perspective. What's causal are not changes in estimators. What's causal are particular patterns in an underlying data generating process. You need to identify those, and you need to learn those. And you can do it directly with Bayesian inference in a joint model, rather than have to go through all this rigmarole with estimators and average treatment effects and the like. All right, so before getting to our third question here, here's my window. From Yair. Let me just briefly answer this question that was asked here in the chat. Let me drop this. So Georgios is asking kind of about intuition being an HMC. So my recommendation, as always, is going to be this little paper right here. This is kind of my attempt to explain the important concepts of HMC, why it scales to high dimensions, and then why we have to implement it in a certain way. And so if you haven't read this is what I would recommend starting with. One of the tricky things with HMC is that it's not... The reason why Hamiltonian Monte Carlo is useful for probabilistic computation is not because it comes from a physics background, right? The physical mechanics of HMC are an analogy. What really matters for probabilistic computation are things like symplectic geometry, which are just rich probabilistically. Like the actual kind of mathematical motivation is completely independent of physics. It just happens that the mathematics that's very useful for probabilistic computation is also useful for physics, right? So it's kind of like, there's this common math down here, and then physics is over here, and probabilistic computation, MCMC, is over here. You can't really directly compare the physics to the MCMC to the probabilistic computation without understanding that common mathematical framework. And I touch a little bit on some of that here, but that mathematical framework does get a lot more complicated. So if you wanted to dig into that, I don't recommend it, But if for whatever reason you were curious, then this would be the paper to look at. This gets into symplectic geometry, and its kind of rich probabilistic structure, and how that can be leveraged to design Markov transitions, and why they're expected to work well in high dimensions. So this one's just a lot more mathy, getting into the kind of full differential geometric construction of HMC. The conceptual intro, this is the one that's much more approachable. And it talks a lot about not just the kind of conceptual motivation for it, why high dimensions are weird, why MCMC is hard in high dimensions because high dimensions are weird, how HMC gets around those problems, et cetera, et cetera. But it also talks about some of the implementation details. Now, if you're using something like Stan, where HMC has already been implemented, you don't have to worry about any of this. But if you're curious, like what a divergence is, what max tree depth problems are, what energy fraction missing information is, those are all touched on here. And then there's a long appendix with a lot of kind of slightly more mathy derivations. So if you're just getting started, that's where I would look. If you studied Bayesian econometrics and you're interested more in doing Bayesian analyses, then I would look at these chapters here, right? This is all my writing on more applied probabilistic modeling and Bayesian inference. With a tool like Stan, if you're using it appropriately, you don't have to worry about how the MCMC works. You just, if the diagnostics are clear, you're good. Then it's more about what model do you want to build, and how do you validate that model, and so on. And that's what all this gets into. It's not public yet, but I do have a giant treatise on Bayesian discrete choice modeling that is in draft form. My Patreon supporters have seen it, or the Covector Plus supporters have seen it. So if you're following along and are curious to get an early view on that, you can join at the Covector Plus level or higher. It's going to be a little bit longer before I have a lot of feedback I need to incorporate to clean that up. But eventually part of it will be released publicly, but that would be something that might be kind of a connection to things you've seen before. But otherwise, just about every topic is treated, and then there's a bunch of case studies that go into actual examples that kind of demonstrate the full procedure of putting it all together. So yeah, give that stuff a try. All right, so our last question here, and actually let me just reload to double check no one has asked any new questions. No. Okay, so so our last question today from Yair is about uniform priors. So already, Yair's question, he's kind of getting at kind of the challenge here. So he says, do you have some time to talk about uniform priors, or as many say, let the data speak? Those are not the same thing. This is, I know what Yair's getting at, but it's kind of the classic problem of people confounding uniform prior with non-informative prior, with ignorant prior, and so on. So I've written about this in a bunch of different places, and I'll just kind of briefly review some of that. So the problem with uniformity, one, uniformity doesn't make sense in terms of, doesn't really make sense in terms of distribution. That's more of a density question, right? And that means that notions of uniformity are always relative to some reference measure. So with, say, modeling a real valued quantity, it depends on your choice of parameterization. Change in parameterization, your reference Lebesgue measure changes, and your notion of uniformity changes, right? So if I have a positive parameter, and I can build a uniform density for that, a uniform measure for that. But then if I transform it to, say, take the log of that parameter to unconstrain it, then what started off as being uniform is no longer uniform. And what's uniform on the log scale is not uniform on the linear scale. So even directly, these questions of non-informativeness and ignorance are really loaded and subtle, and they don't really have easy answers. I think the best way of formalizing this, and there may be some bias here because I'm trained as a physicist, and so I often think about things in terms of symmetry. But I really think that is the right way of thinking about uniformity and ignorance. Right? A distribution is more uniform, is less informative, is more ignorant if it allocates the same probability to more and more equivalent subsets. Now, the challenge here is defining what these equivalent subsets are. And often, this is best done in terms of symmetry. So, for example, on a discrete space, the classic transformations that you might consider are permutations. Right? You can just change the order or change the labeling and indexing of your individual elements. And if your probability distribution is the same, if all of your probability allocations are the same, regardless of how you move those individual elements around, then you have a pretty uniform, but also a pretty non-informative probability distribution, because it does not distinguish any one element from any other element. Right? They're all treated the same. Now, on continuous spaces, like the real line, real planes, and so on, permutations are no longer possible. You can't construct... There's no measure, let alone a probability distribution, that's invariant to every permutation of the space. So we have to think in terms of a more restricted set of transformations and ask, can we build a prior that's symmetric to those transformations? And this is where, again, we start seeing there's a bunch of arbitrary choices. So if you fix a parameterization of a real line, you can ask, can I build up a model that's invariant to translations? And the answer is yes. That's, in fact, what the Lebesgue measure is. Can you build up a model that's invariant to scalings? Kind of, sort of. The Lebesgue measure is kind of, sort of invariant to scalings if they're finite, and you don't care about the total measure, right? So if you kind of like are only interested in relative allocations, scalings can kind of, sort of be okay. On a positive real line, again, if you fix the parameterization, now you can't. There's no measure that's invariant to translations, because if you look at any translation, you're going to take a set of positive numbers and translate to a set of negative numbers where your model isn't defined. But proportional translations, scalings, those are okay, and you can come up with models that are invariant to proportional scalings. That's what, like an exponential model is one of its key properties is invariant to probabilistic scalings. I should say it's closed under probabilistic scalings. But these are, why those transformations and not any others? And what I like about, kind of like with the probabilistic model discussion that we just had, it changes the conversation, right? In the causal inference discussion, instead of saying, what's the causal effect, and can I identify this, et cetera, no, you dig into the model, you get this very nuanced perspective, and you can make these very precise assumptions about what are the behaviors that are going to persist, right? And you have to take the responsibility of making those assumptions. The same thing is true when we're talking about things like non-informative or ignorant probability distributions, measures, and so on. Because we can't construct a universally uniform / ignorant / non-informative model, we are responsible for defining what are the symmetries of interest. What are the relevant symmetries that encode the relevant notions of ignorance? And then can we build up a model that's compatible with those? And so if you think translations are the relevant thing, you'll get to a Lebesgue measure. And then that means that you want a probability distribution that's as close to the Lebesgue measure as possible. We'll come back to this in a second. Can't do that. There is no probability distribution that looks like the Lebesgue everywhere, because the Lebesgue integrates to infinity and not 1. A more subtle example of that is exchangeability. So exchangeability, we can think about this as a certain kind of transformation, or invariance to a certain kind of transformation. Can I build up a model for a set of parameters that's invariant to permutations of those parameters? And what Dave Finetti showed is that as the number of elements grows, as your population of things that you want to build a model for gets larger and larger, the all of the models compatible with that exchangeability symmetry look more and more like the a hierarchical model. And so we use hierarchical models because they are the kind of appropriate notion of ignorance under exchangeability, under that particular kind of permutation symmetry. And it doesn't look like a uniform model, right? It doesn't look like what we think of as a non-informative or ignorant model, because it's a very particular kind of symmetry that we're considering. And that's kind of the beauty of all of this, right? Is that if you step back and recognize there is no universal notion and you have to kind of define the kind of symmetry that you want, one, it prevents you from making bad choices, but two, it can sometimes help identify things that you never would have considered before, right? If you're stuck in this notion that uniform means flat, or a non-ignorant means flat, then you're going to miss out on a lot of very powerful prior models you could be using, because your domain expertise is really more consistent with a more subtle notion of non-informativeness or ignorance. So again, I really like this notion of symmetry as a way of saying, like, of making the discussion of a non-informative prior more constructive. You can't, instead of, so if somebody comes to me and says, like, I want a non-informative prior, no. What's the symmetry you care about? Let's start there, if that's in fact the road you want to go down. That said, in practice, there's almost always information available to build a weakly informative prior model. Everyone says they don't have any domain expertise. And I think what often they mean by that is that they cannot elicit a perfect representation of their domain expertise. And because they can't build a prior model that perfectly captures what they're thinking implicitly in their head, they can't build a prior model at all, so they have to rely on some default. The more practical reality, or the more productive approach, is to take this Goodian approach. So I.J. Good, still to this day, one of the only writers of Bayesian, only Bayesian writers out there, who kind of makes the point that, look, building a prior model is expensive. It takes time and effort to translate what you know implicitly into an explicit mathematical form. And so there's layers to how much to the prior models you can build depending upon how much effort you want to put into it. You put a lot of effort into it, you can get a relatively precise translation. You put a little effort in, you can get a relatively imprecise translation. But that imprecise translation is still going to be a very useful prior model in a lot of cases. And in fact, it's going to look not very uniform. Right? So if you can think about a lower threshold and an upper threshold that you want, that like the reasonable behaviors are contained within, and you can build up a very heuristic prior model that's consistent with, that concentrates within those boundaries, you're done. You've done most of the work. So often, if you kind of step back a little bit and ask why somebody is interested in a non-ignorant or a uniform prior, you can often, if you kind of change the problem around and say, like, what do you know? Don't tell me, I don't have to worry about everything. Like, is there any information that's available? Is there some point where things get too weird to be realistic? If you can get that information out, then this whole conversation becomes irrelevant because you're not trying to build a non-ignorant uniform prior anymore. If somebody wants to go down that road and says, like, no, I don't want to bias this, I don't want to influence this, I'll make assumptions with the observational model, but heaven forbid I make assumptions with the prior. Well, that you're kind of dealing with like a false disequivalence, false separation of those assumptions. But if they have to go to that road, then you can frame it in terms of symmetries. And ask, okay, well then you're responsible for defining the symmetries that matter here. And then we can try to come up with a prior model that respects those symmetries. That said, in a lot of cases you can't. And so this is the classic problem with the uniform prior model. So if you have certain parameterization of a real line, and you say, well, really what I want is translation to, or is symmetry to translations. Now, the Lebesgue measure is symmetric to translations. That's great. But the Lebesgue measure is not normalizable. Right? The total measure of the Lebesgue measure is infinity. And so you can't divide the Lebesgue measure by infinity to get a probability distribution or a probability density function. And so there's fundamentally no way to construct a probability density function that's symmetric to all translations on a real line. Which means there's no prior model that we can build based on this particular notion of ignorance. Now, we can be a little bit sloppy and say, like, all right, well, but what if I just put in a uniform measure as my prior model? Do I still get a probability distribution out as my posterior? In a lot of cases, yeah, you will. But not always. So there's two questions here. One is it okay to use a uniform prior density function as a prior model in the hope that the likelihood function will compensate and give you a well-defined posterior? And the answer there is it depends, right? Like, you're going to get burned eventually. And the question is, what's your risk threshold? The other way of approaching this is to ask, well, what's happening when the posterior is still well behaved? And this gets into this argument from Box and Tao that what's happening is not that you're actually using a uniform prior model, but rather your uniform prior model is approximating a very diffuse prior in the context, in the neighborhood of your particular likelihood function. So the classic demonstration of this is you have a very narrow likelihood function relative to your prior. And when you zoom in and look at the peak of that likelihood function, the difference between your diffuse prior density and a uniform density are very, very similar. So when you get a well-defined posterior using a uniform density instead of a uniform, instead of a well-defined probability density function, you have really the right way of thinking about it as an approximation to a diffuse prior model. And this argument comes from the infamous Box and Tao. Love this book. So this book, just to make it very clear, this is a newer edition, right? But this is a reprint of the 1973. Try to get that in there. So this book is now like 50 years old, and it was written before all of the famous Bayesian textbooks that everyone reads these days. And if you go to page 22/23, oh look, it's a discussion of uniform prior density functions as approximations to locally diffuse prior models. So just the, like, in the above, we've used the word reference prior. In general, we mean by this a prior which is convenient to use as a standard. Great terminology. In principle, a reference prior might or may not be dominated by the likelihood. But in this book, reference priors which are dominated by likelihood are often employed, right? So now, the reason they're even discussing this is that this was in the days before personal computers, let alone MCMC proliferation. So they had to do everything by hand. Later on in the book, they do a 3-component ODE model entirely analytically. It's wild. And one of the ways they get it all to work is to have a lot of conjugacy in the observational model, a lot of kind of summary statistics and kind of analytic simplifications, and then they often use uniform density functions, right? But they're doing it as an approximation. Every time they do it, they go back and check to make sure that the likelihood function is well behaved, right? There's a lot of kind of care and effort that's put into this because they're using it as an approximation. And not only do they talk about, there's a whole section of difficulty associated with locally uniform priors. That's about all the kind of bad things that can happen. It's so good, right? They also get into Jeffreys priors, which is a more subtle notion of transformation I didn't mention here, where you transform the reference measure as well as the density, so things kind of stay even more symmetric, but then get harder to implement in practice. And it's all in here, right? And it was, over almost 60 years ago at this point. Wild. So a lot of what I'm writing here is just kind of a reflection of some of the discussion in Box and Tau, but you can also just pick up your own copy and read it. And it still holds up. Like, the only thing that doesn't really hold up about this book is that they're doing everything analytically and not using modern computational tools, which you have to give them credit for, because, it was published in 1973, right? So it's probably written in the 60s and early 70s. But these days, we don't have to do that because we have tools like probabilistic programming and MCMC, where there's no cost to putting in a weakly informative prior model. It's just thinking a little bit about the thresholds where things start to get weird, and then building a prior model that concentrates within those thresholds. It's not that hard to build a useful prior model. I think what happened historically is, you had people like Box and Tau and others who were using these uniform density functions as prior models in a very careful, responsible way. Right? They're interpreting them as local approximations. They're validating the local approximations. They're ensuring that the likelihood functions are always really narrow and dominating the structure of the posterior. They're not, when the likelihood function is not identified, or when the observation model is not identified, so the likelihood functions become degenerate, they're not using these prior models, or they're not even using those analyses, right? So it's a lot of experimental design choices that go into it. Just all kinds of care that we don't see today. And then I think what happened is people started, learning statistics as routine. And what they saw is, you put a uniform density down, and then everything goes well, and you get your answer out, right? They lost all that nuance and that care that went in, that was around those basic practices. And then at some point later, there becomes this like post hoc rationalization for we're doing this now. There has to be a reason we're doing it. And instead of going back and reading and understanding what people were doing, it becomes this, we're doing it for a principled reason, because we want things to be uniform. And it gets into this whole terrible feedback of bad conversation discussion that's just the worst. And there's this last bit here. This is just a fun conversation about how the real line is weird in ways that are kind of obvious but also counterintuitive. And this demonstrates the what goes wrong. So if your likelihood function doesn't concentrate very strongly, if your data don't inform a particular parameter, that you have a uniform, you're using a uniform density to approximate a prior model for, what happens? Well, in that case, your posterior density just looks flat, right? And the problem with a flat density function is that it doesn't concentrate in the way we think it does, right? It sort of doesn't concentrate around a peak. But then you might think, well, that means it's flat. There's no concentration at all, right? Well, not really. It does concentrate, but it concentrates around infinity, right? And the argument I like to do is to say, like, all right, well, how much of this approximate prior density or prior mass, prior probability is above 1? And you'll be like, well, infinity, because 1 to infinity, there's infinite, Lebesgue measure out there. All right, but what about between 1,000,000 and infinity? Shouldn't that be less because you're so far away? Like, no, but it's the same infinite amount. What about between 10 quadrillion and infinity? It's the same infinite. So there's no matter how far you go away from zero, there's always infinitely more prior mass past that threshold. And that's why there's this notion of concentration around infinity. You keep going and keep going, and there's still more. There's still more to go. There's still more to go. You're never going to reach kind of a saturation probability until you hit infinity. And one way of thinking about that is kind of unrolling the real line, or if you have a plane, the whole plane, into a circle or a sphere. And you think about infinity as just kind of just point on top. So kind of positive infinity and negative infinity roll up together and touch. And if you think about it from that perspective, you can see that there is this literal concentration of that uniform density around infinity, right? When you roll things up, everything gets squeezed towards infinity. And from that perspective, you might look at it and go like, well, I don't want that. I want it to concentrate around closer to zero. Shouldn't it be more balanced? Well, that is balance. That is uniformity, right? Uniformity doesn't behave the way you might think. Because what you're often thinking about is uniformity within a local neighborhood. But uniform everywhere does not mean is not quite the same thing as uniform in a local neighborhood. And so again, I think it's much more practical to think in terms of thresholds where things get weird, and then a model that's close enough to being diffuse enough that it's basically locally uniform within that neighborhood. So now you get all the benefits of not having to think too hard about your domain expertise, letting the likelihood function dominate if it needs to, or when it can, but also having safeguards in the case of one, your likelihood function not being very informative for a particular parameter, and have given that containment by that prior model. And then two, if your model is misfitting or it's contorting in some weird way that moves it outside of those thresholds, you'll see that because there'll be a tension between the likelihood function and the prior, right? And that will indicate that your model's contorting itself in a way you don't want it to. So these are just all part of the problem here is assuming there's a notion of a default prior you have to think about, right? And as Box and Tau talk about, like you can have a prior you start with, but you're responsible for validating that prior is going to be adequate in a given problem. And by thinking just a little bit harder than a default uniform density, which sometimes kind of sort of gives you a good result, and thinking about things like thresholds and concentration within thresholds, you can get a lot of the similar behaviors to that uniform density that you want, but also a lot of safeguards. Just a little bit more work, and you're going to get a well-defined prior model that you can be pretty confident in, that safeguards you, but also allows the data to speak if it has something to say. So there's a lot of kind of different points here we've covered, a lot of different approaches, and I think it all comes down to the fact that notions of uniformity, ignorance, non-informativeness are not well defined. And so depending on how you define them and their relation to each other, you get all of these different perspectives. Some of which might be more intuitive, some of which might be more applicable in a given circumstance, and so on. But again, you can sidestep it all by just not forcing any of that. Not trying to come up with this idealized, non-ignorant prior model, recognizing the utility of just even a little bit of domain expertise and incorporating that. All right, guys. Sorry. So there were some questions here. So she's asking about, is this related to maximum entropy principle? Not quite. So maximum entropy is a different kind of consideration. I guess it is sort of related. So I mentioned a little bit earlier that, well, I mean, it might. Let me just say it explicitly to put everything together. So let's say we are thinking about a model, some kind of probability distribution that's symmetric or that's invariant to translations, and we realize, oh no, we can't do that on the real line. There is no probability distribution represented by any probability density function that is normalizable and symmetric to translations. Now we have this little big measure that's symmetric translations, but it's not normalizable. What if we ask a slightly different question? What is the probability distribution that's closest to the Lebesgue measure, but still is normalizable? Now, it turns out that's not that by itself is not a well-posed question. There's not enough information to provide a good answer. But if we add some constraints, then we can answer it. So on the real line, for example, if we impose two constraints, and we say, all right, can we talk about the closest probability distribution to the Lebesgue measure, this uniform reference measure, that has a particular mean and a particular variance. So now we have three constraints. It has to integrate to 1, its mean has to be a certain value, and its variance has to be a certain value. That you can formulate as a variational problem, and the answer is yes, you can in fact do that. There is a single probability distribution represented by a particular probability density function that integrates to 1, that has a certain mean and a certain variance, and is as uniform as possible under those three constraints. If you drop any one of those constraints, if you drop the mean or the variance constraint, either of those moment constraints, then there's not a single unique answer anymore. It becomes just a very weird variational solution. But if you have those two constraints, you get a well-posed answer. And that is maximum entropy. So where the entropy comes from is the entropy is characterizing the distance, quote-unquote, the difference between the uniform measure, your reference measure, and your distribution of interest. So it's trying to search through all the possible distributions to find the one that's the closest to that measure. And entropy flips a sign, and so you're getting maximum instead of minimum entropy. But really, the better description of it is it's minimum relative entropy is what you're doing. Because you're trying to find the distribution that's closest to that reference measure under certain constraints. And I do write about that here. No. These chapters are gonna be rewritten at some point. But here I talk about kind of from just a high level what we're actually doing with maximum entropy. You set up a variational problem using the KL divergence as your target, as your measure of closeness. Your reference measure is fixed. Your nu is fixed. And now you want to find some mu that is closest to nu, that minimizes the KL divergence. In general, there's not a unique solution, so you have to add some constraints. So because we want a probability distribution, we always want to add the normalization constraint. And then we can add additional moment constraints or expectation constraints. It's like polynomial expectation constraints. If you have enough constraints, you can get a well-defined answer. So things like a lot of families of density functions can be derived from this perspective. And so they give us a way of thinking about up to a certain moments, it is as uniform as possible. And so you can, those can be useful if you want something that's like, it has some structure, but not any more structure than that. Now, what's interesting about that is that when you go through that construction, what you actually derive are not just things like the normal, you derive the entire exponential family. So the exponential family of families of density functions include basically all well-defined density functions. They include all of the things that have summary statistics, finite dimensional summary statistics. They include all things that have like really nice properties like log convexity. They're just like the ideal behaved family, and it turns out they're equivalent to this maximum entropy approach. But again, that big difference is that it's not just asking about the thing that's as uniform as possible. It's or as close to a given reference measure as possible. It's as close to a given reference measure as possible up to constraints. And so tying back into the previous conversation, it's a little bit different in the sense that you have to define what the reference measure is, right? And that's where your notions of symmetry come in. What does it mean to be a nice, symmetric, uniform reference measure? Great. You're responsible for choosing that. That defines the reference measure. And then there's constraints you have to impose to make the variational problem well-defined. In some cases, it's one moment. Some cases, it's multiple moments. Some cases, you can add more moments and constrict the problem even further. But that will then eventually give you kind of your well-defined variational solution. So, yeah, tangential a little bit, but hits at some of the same problems where, maximum entropy doesn't give you a single black box answer. There's not a default, right? It's a way of clarifying under a certain set of assumptions, you get to a certain result. And what's nice about it is you then know what assumptions that you have to make and whether or not you feel confident in those assumptions model to be useful. And then your second question here from Ju. So they're mentioning the paper unifying and canonical description of measure preserving diffusions. So this is a bit of a sore point a little bit. So that paper was all about characterizing all possible measure preserving diffusions on a manifold up to certain constraints of practicality. That was actually a special case of a much larger paper we wrote about characterizing all measure preserving flows on a manifold. And the goal of the paper was to understand how much you can generalize Hamiltonian Monte Carlo. So actually it ties a little bit to, Georgios was asking about, or Georgios was asking about the kind of math behind HMC. Well, one of the mathematical motivations for it is that what you're constructing is a measure-preserving flow. And measure-preserving flows explore probability diffusions extremely efficiently, no matter how many the dimensionality you're working in. And so all of the symplectic geometry that happens to look like physical stuff, mechanics and all of that, that's just an accident of a way of deriving measure-preserving flows in a very systematic way. Give me a distribution. Can I construct a flow that preserves that distribution systematically? And that's what HMC does. So the natural question is, are there other ways of constructing measure-preserving flows on a manifold? In particular, are there other ways of using differential information, gradients, to construct those flows? And so the paper we put together with Alessandro Bart, who's doing a lot of the kind of mathematical push there, was characterizing all of it. So you can completely characterize all measure-preserving flows that are generated from vector fields. You can completely characterize all flows that are derived from differential information, first-order differential information. And then you can look at the intersection of those two groups, and that completely characterizes all measure-preserving flows that you can derive from gradient information. So ignoring things like higher-order jets and stuff like that. And then you can ask, well, within those families, what possibilities are well-behaved? And basically turns out HMC is the only one. Like, there are other possibilities, but they're weird and very awkward to work with in practice. The symplectic geometry that HMC is based on is just perfect. It has every nice property you could ever want. So it's kind of an accident that it was found first, but it does look like it is the optimal approach. Now that paper, and then we took, I put so much work into this. In addition to all of the math, then we actually had algorithms for like, okay, here, make choices of these differential geometric objects, and here's a generalized version of HMC. Here's a generalized version of dynamic HMC, and like, taking all that stuff and writing it generally and getting, the proofs of it being target preserving and all of that. It was great. And at one point it was up to like 300 pages. It was huge. And unfortunately, I have not been able to contact my co-author in some time. For a while I was pushing to get it published, or not even published, like put it on the archive. Like, let's just put it out there. I don't care about publication. Let's just get like a stamp on it, because there's a lot of cool stuff here that people would enjoy, like that one archive paper that is up there, which is just a snapshot, tiny snapshot of all of the stuff that we were talking about. But the lead co-author, who was really the main author on this paper, right? I was kind of there to try to make it, craft it into something, the discussion to be a little bit more conceptual, readable, and then having the algorithm stuff at the end. But he was the one putting all the math together. He wanted to keep generalizing it, and to the point where it was like, it was not just manifolds, it was like these very general notions of a manifold, groupoids and stuff like that. And stuff was getting added, and then it got to a point where he was overwhelmed with other stuff, and then kind of, I have not been able to get in contact about, like, literally doesn't respond to my emails anymore. So there is a great, exciting paper out there that really kind of clarifies the optimality of Hamiltonian Monte Carlo and a lot of these things. And I don't know if it's ever going to see the light of day, which is sad and it's frustrating. But I'm not the lead author on it, and I don't have any authority of the other author, and so I don't know what's going to happen to that. But if that ever gets out there, I'll absolutely do. What I'll probably do is like what I do with a lot of the papers I put out, because I don't really care about publication. I'll throw something up in the archive and I'll do like a video review on Patreon. If something like that, I'd probably break it down into multiple video reviews, and because it's a research paper, I'd definitely be made public. So if that ever happens, you'll hear about it on my mailing list, or I'll blast it on socials, or definitely mention it on the Patreon. And I would do some kind of series of talks on it, live stream talks like this on it. But it has to come out first, because it's not really my paper to do with that on my own, But it's very cool, and I hate to say like, oh, it's I know it's kind of a tease thing to do, but like, the math in there is so awesome. It's so neat how these spaces get characterized, and it's such an elegant construction with the intersection and all that stuff. And then the higher level constraints, it's really really neat. And maybe it'll make it out one day. And if it does, I'll definitely talk about it. But until then, yeah. No, so JD's asking if that paper would be relevant to the new algorithms he keeps hearing about. No, so the paper there was all about kind of the underlying geometry and the basic construction of the algorithm. What you're seeing these days are kind of different ways of implementing that geometry. And I don't think any of them are all that productive. I think a lot of the comparisons that are being made to argue for them aren't that impressive, and then they're kind of bad comparisons because they're comparing one very highly optimized thing to a not very highly optimized thing for the problems that are being compared. So those are it's things like adaptation of the step size, or adaptation of the mass matrix, or the inverse metric, I should say. Right, those things are not part of the like deep differential geometry of HMC. The geometry of HMC says you construct a measure preserving flow, and then you have some kind of degrees of freedom you can choose, and then you have to discretize that measure preserving flow, and there's some additional degrees of freedom in the discretization. There's not much discussion, regardless of kind of how you change the back end, you're still going to have those problems to deal with. And then how do you deal with them in a way that kind of preserves the Markov invariance of the transition? Those are kind of orthogonal to that particular kind of deeper mathematical foundation. And so, like, one of the things that was neat about the paper is that kind of because some of those things are orthogonal, like even the dynamic integration time, that's kind of orthogonal to how what kind of flow you're integrating to expand your trajectories. And so one of the things that we had in the paper was a general algorithm that said, give me any measure preserving flow, and here's how you would do a quote-unquote nuts-like construction in it. And it was pretty straightforward and pretty elegant. I mean, there were some subtleties in how you had to put it all together to make things fit in. But again, those are just things that kind of add on or orthogonal to the kind of deeper foundational pieces. So none of that would really change. Yeah, again, the paper was so good, Drew. I don't know. I'm gonna be sad now. I haven't thought about it in a little bit. It's really unfortunate. That some version of it isn't out there, because it is fucking brilliant. And I'm clearly frustrated a little bit with my co-author, but like the work he put into it was wild. It just really really cool math, pulling it from all kinds of different places. And the final art kind of construction of the paper, the flow of the paper we had was just so fun to read if you're into that kind of math stuff. So hopefully one day. All right, so with all that said, we've covered the 3 questions that were asked. Thanks to JD, Zach, and Ayir for asking those questions. Great questions. A lot of fun stuff to talk about. Give me excuses to rant about things. Thanks for everyone in the chat asking questions. I'll give one last opportunity here. Are there last questions people wanted to ask about anything as we're kind of winding down? About kind of small topics, maybe small questions, or anything related to the discussion that we've had so far. And as a reminder, if you're watching the VOD after the fact, you can always post questions in the Patreon comments, and I'll answer as much as I can. You do need a Patreon account to post comments. You don't need to be a paid supporter. Free supporters is fine. That'll give you access to these posts, to the off-star posts. But the VOD you can watch whenever, without a account. So just be aware of that. All right. All right. So there's one last question from JD. So JD's asking, probability chapters working on new ones or just updating? Both. So I'll just give you a hint. So I have recently updated chapters 1 through 4, doing kind of minor style updates, typo corrections, formatting corrections, things like that. These were already updates, chapters I had previously written, but kind of in a more kind of proper form. I have currently, but not yet updated, to the website. I have gone through and cleaned up chapters 5, 6, and 7. What I have been stuck on is chapter 8, which I'm actually splitting up into 2 different chapters. And then the second of those chapters on conditional probability density functions is getting a lot more discussion. So there's a new example in there, as well as kind of a much better description of what's actually going on. So it's just one of those things where I wrote it, and it wasn't wrong, but it really wasn't as... what's the word I want to use here? There were steps that were skipped, and the steps are definitely subtle, but they're important because they actually connect the abstract mathematics to what we're doing in practice. So when we talk about disintegrating a Lebesgue measure, what does that actually correspond to in the calculations we do? So I can show the examples, but if you really look at them for more than a second, it's not clear where I pulled this stuff out of my ass, basically, right? So this is requiring some work to clean up. And I'm pretty sure I have all of the math. It's just that I have to reformat, reorganize the chapter a little bit, go through and clean up some notation, and the like. And that will then change some of the references in the previous chapters, which is why I haven't posted them yet. So that's going. And then once that is done and cleaned up, that'll set the stage for doing chapter 9, probability theory on product spaces. That's going to be an update of this chapter down here. But it's going to be much more, it's going to be cleaned up using better notation that was established in these initial chapters up here, these updated chapters. It's going to talk about a little bit about some of the theoretical considerations and why product spaces are so nice, but then really start getting into the practical side of things. That then sets the stage for 2 new chapters. One is going to be on... more heuristic introductions to probability theory. So it's thinking about probability theory, like learning it from density functions as being first-class objects, and then learning it from this kind of random variable notation. How does that tie into the more foundational approach I've taken in these chapters, and what are some of the consequences of that, things you have to look out for if you want to go in that direction? Kind of like a translation of, if you learn probability theory through density functions, how does that tie into what we've talked about so far? So just a lot of kind of, just a check-in translation kind of a chapter. Then there'll be a chapter on ensembles and conversions. So it's going to be kind of like the first few sections of the sampling in Monte Carlo chapter, as well as some of the discussion in the common families of probability density chapter. about notions like convergence and central limit theorem, stable distributions and things like that. Then that will set up for an updated families of probability densities chapter. Then the updated sampling in Monte Carlo chapter. Then we'll move into problems of computation in high dimensions, and not just one chapter on Markov chain in Monte Carlo, but I think like 5. So there's going to be one on kind of the basics of Markov chains, engineering Markov chains to preserve a given target distribution, and getting into things like Metropolis Hastings. So like Markov chains, Markov chain Monte Carlo, given a particular Markov chain. And then how do you engineer a Markov chain or Markov transition to preserve a distribution of interest so you can estimate the expectations you actually care about? That's where we'll get into things like Metropolis Hastings and tuning a transition and the like. And then there'll be a chapter on Hamiltonian Monte Carlo, where it'll be like a complement to that conceptual paper I mentioned earlier, but it'll be a lot of like code demonstrations of coding up a basic HMC in R and showing consequences there. So there's the plan is there, it's all there, and it's just time, and I'm getting to it. Particle-based methods, I'm not a fan. They can work. Let me put it this way. I think they can work okay in some applications, but in general, the idea of throwing particles into a problem doesn't solve the issues that one usually has. Another way of saying it is the limitation of most MCMC-based methods is your Markov transition. How effectively is it at exploring your target distribution? Particle methods don't solve that problem. Adding thousands of particles isn't going to help if you still can't explore your target distribution effectively. All something like SMC does is that instead of looking at one target distribution, you might break it down into a sequence of target distributions that are maybe easier to work with, but in practice they often aren't. And your limitation is still what your underlying Markov transition is, right? So it's not the number of particles you have, it's how good you are at moving those particles to update them from one step to another, from one sequence, iteration of your sequence of target distributions. And that is just as hard as trying to target your target directly. So I don't, they work okay in circumstances where modeling the joint is going to work okay anyways. Like if you hit a Markov model, just fit the whole thing jointly. It works fine. You don't need the particle method on that. Even if you have a super high dimensional problem, it's going to be fine. So I'm not a huge fan. And mathematically, they're very interesting. There's some cool stuff you can do with that decomposition and ways of framing SMC and particle-like methods and the like. But in terms of practical application, I don't see a lot of huge utility. And so I certainly am not going to spend a lot of time writing about it. If in a future office hours, I'm happy to talk about it and chat about it a little bit more. So keep that in mind. But yeah, my focus in all of this is modeling and inference, right? Like I come from an applied science background. That's what I really care about. That's what I really get excited about. As maybe you might have seen earlier when I was talking about the causal inference stuff. And so for me, the HMC and the problems of computation stuff, that was all that was needed to do the probabilistic modeling. Like historically, I started getting into HMC when I was trying to write an MCMC code for my thesis analysis in grad school, and I started digging into the theory of HMC because everyone said to use it, but no one really knew why it worked, and it wasn't clear if this was actually going to help me solve the problem or not. And so all of this was kind of an end around of getting a tool that we can bring to bear so that we can focus on what model we want to build. What's our data generating process? How do we model the data generating process? How do we utilize those inferences and so on? So that in terms of my writing here, that's the focus. So it's not to me that's the only focus or that's the only thing people should care about. It's just what I care about, and hence what I'll be focusing on. And then the last thing I'll mention is for those who are watching who are Covector Plus supporters, There's a surprise coming. It's going to take a few days, but there will be a substantial piece to hit that should be fun. So keep an eye on that. And then for those who aren't Covector Plus supporters over on the Patreon, it'll get released sometime in a month after it gets posted on the Patreon. So sometime in July, probably. So keep an eye out for that. Keep an eye out for the updated probability theory chapters. It's going to be the focus for the rest of the year. The main focus for the rest of the year. Thanks for all of the questions and chat and discussion. And let's do it again sometime. Cheers.